Hi, I'm going to do an example problem from Chapter 13 on equilibrium, demonstrating the use of the ice table and the quadratic formula in solving for equilibrium concentrations. The example I'm showing is I have 4 moles of hydrogen iodide. I'm going to place it in a 5-liter flask, heat it to 800 Kelvin. I'm going to monitor the following reaction of 2 hydrogen iodide molecules are in equilibrium with hydrogen and iodine, providing the equilibrium rate constant equals 0.016 at 800 Kelvin. So let's draw a quick sketch of what we are looking at here. Everything here is also in the gas phase. I'm going to specify that in. So I'm going to have a flask, initial, and it's got some HI molecules in it. So my HI molecules are then, over time, to reach equilibrium. This is what we're trying to find out. We're going to have some question mark combination of molecules at equilibrium. So we'll have some amount of HI, hydrogen, and iodine at equilibrium. We're going to solve this using the technique of the ICE table. ICE stands for initial change equilibrium. We're going to put our species up here: hydrogen, iodide, hydrogen, and iodine. And we're going to put in our initial conditions. Remember, we're talking in terms of molarity. We're going to put in initial concentration. So we're going to convert our moles to molarity. I have molarity as moles per liter, so I'm going to end up getting 0.8 molar hydrogen iodide. Please ignore my sig figs. It should have 3, but I'm going to just truncate it to make my work a little bit less messy. And initially, at the beginning, all I have is hydrogen iodide. So I have 0.0 moles of hydrogen and 0.0 moles of iodine at the beginning of my process. It doesn't explicitly say that in the problem statement, but it can be assumed based on how it's written. It just tells you the HI is present, so you can assume that there is no hydrogen or iodine at the beginning conditions. At this point, we can write our mass action expression. We're going to call it Q just because we're not necessarily at equilibrium here. And that's going to be hydrogen, concentration of hydrogen times the concentration of iodine divided by the concentration of hydrogen iodide squared. That squared, remember, is coming from the 2 in the coefficient of our reaction. So it's important when you're doing this that you are always working with a balanced reaction. The initial Q, so at the initial conditions, Q is going to equal 0, because my hydrogen is 0 times 0 over 0.8 squared, and that's just equal to 0, which is less than K. And what that means is the reaction is going to have to proceed to the products. That is always going to be the case if I don't have any products, so you don't really have to go through the exercise of calculating Q in this case. But it's good to point out that, you know, depending on what you have at the beginning, you can calculate Q and figure out which way the reaction is going to go. So in this case, I'm going to have to produce products. So when I go to complete my ice table with my change, I know that I'm going to lose reactants and I'm going to gain products. So here my HI, my hydrogen iodide, is going to change by 2. Again, I have to account for that coefficient times some number x. And then I'm going to produce some number x of hydrogen and some number x of iodine. And at equilibrium, I'm going to have 0.8 minus 2x, x, and x. So that completes my ice table. At this point, we want to go ahead and complete and put our equilibrium coefficients into our mass action expression. And we're going to go ahead and solve that, where we have K 0.016 is equal to x squared over 0.8 minus x squared. Now we need to look into the algebra to solve this expression, because the whole idea is to figure out what x is going to be, what our equilibrium concentration is going to be. So first, whenever you're approached with this type of problem, we're going to try to make the assumption, of a small x. We always want to start here because that's going to make our algebra much simpler. I can tell you it doesn't likely look like it's going to work. K, really to be small, is going to have to be 10 to the minus third, 10 to the minus fourth. But let's go ahead and see what we get out of this, and it will give us at least a good ballpark of where our answer is going to end up. What I mean by making this small x expression is that we're going to say basically that 0.8 minus x is going to approximately equal to 0.8 molar. So when we go to solve for x, we can get that this is a small. It's small but non-zero, and that's an important distinction when you're solving these. So you can get that K is approximately 0.16 equals x squared over 0.8. Don't forget to square that. And you go through the algebra. So we have 0.016 is equal to x squared over 0.18, and the algebra gives me x equals plus or minus 0.102 molar. To validate our expression, here is obvious that the negative x is clearly not possible. So x has to equal, because I have negative concentration, 0.012 molar. We have the 5% rule. Which says basically if x is less than 5% of the initial concentration, then this is a valid assumption. And so we can look basically at 0.102 divided by 0.8, and that's about 13%. So unfortunately in this case, small x is not valid. So does that mean I did all this work for nothing? Absolutely not. This gives you a ballpark of where x should end up, as well as if you're in a multiple choice scenario, this may be enough to narrow down your multiple choice answers to one that you can figure out is the correct one because you are close enough. So let's go ahead and solve this even though my small x assumption is not valid. We will solve it with the quadratic relationship. So let's once again write down our k expression. So again we have, get rid of the red. So 0.016 equals x squared over 0.8 minus x squared. Solve for x. This ends up being a little bit of algebra to get it in a form we can deal with it. It's going to equal x squared. After some math, you can get this to 0.936 x squared minus 0.0512 x plus 0.0 0.01024 equals 0. Now I have it in a form to use the quadratic equation. Our friend x equals negative b plus or minus the square root b squared minus 4ac all over 2a. In a homework situation, I encourage you to use online calculators to solve this. It can be tedious, but you should be comfortable with it. When you put it into the quadratic formula, you solve that x is equal to 0.08076 molar or negative 0.135 molar. Again, we can automatically discount our negative root as not feasible. So this is somewhat close to our initial approximation of 0.1. But you'll notice that it is a little bit different if we, because the small x was not a valid assumption. It's a good idea to put this back into your original ICE table. Now we know the numbers. So we have our species. And we had 0.800. Our change now, minus 2x. So it's going to change minus 0.16. And this is going to change positive 0.08, positive 0.08. And so our equilibrium is going to be 0.64 molar HI, 0.08 molar H2, 0.08 molar I2. And we can always put this back into our original expression to make sure we get the same answers back. So 0.08 squared over 0.64 squared. And we get 0.016 back. So our work checks out. And that solves this problem. So as I said before, continue to practice these guys. They can get a little tedious, but the main thing, you can always check your answer at the end, so you should always be comfortable with your answers once you've gone through all the math and solved them out. This technique is very important. We're going to use this technique through the next 3 or 4 chapters in solving acid-base problems, because all these problems are going to be equilibrium driven. Alright, I hope everybody has a great day. Don't hesitate if you have any questions.